Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your ZyBooks Section 2.2 titled Matrix Multiplication. Right, so in the last section, 2.1, you learned about some operations with matrices, matrix addition, and scalar multiplication, where you multiply the matrix by just a number. In this section, we're going to see how and when do we multiply matrices by other matrices. All right. So there's this figure that the section starts with, and they never refer to it again, I don't think. So I'm actually going to come back and talk about this once we've established how to multiply matrices, right? Because it's I got a couple matrices here with number. This is like a 4x3 matrix where you have your teams of a business, of a company, and then their sales or sales goals. I'll just say sales of each product that they produce. And then you have this matrix representing the manufacturing costs, like what's the cost of each of the materials and shipping and packaging and labor, materials, labor, packaging for each product that they produce, and you get this 3x5 matrix here. And I'll show you how are we going to how can we relate these matrices in multiplication, and what will that multiplication mean. All right, so you got your objectives. All right, so first, the size of a matrix product. All right, so this is when you multiply a matrix by another matrix. There are some size requirements, right? So if you recall, for matrix addition, the size, when you added or subtracted two matrices, the matrices had to have the same exact size. That is not the case here. All right, for matrix multiplication, say we have an m by n matrix called A, can only be multiplied by an n by p, right, where p is just some other number, matrix B, to yield an m by p matrix A times B. Right? So you see that if I do A times B, see the number of columns of the left matrix has to be the same as the number of rows of the right matrix. Right. So if the number of columns in A is not equal to the number of rows in B, then the product A times B is undefined. So the size requirement is kind of in this box here, right? If you take an m by n matrix and multiply it by another matrix, the number of rows in that second matrix has to be the same, right? Must match the number of columns in the first matrix, the left matrix. And then the final result, see, will yield an m by p matrix. The final result, the size of the product, will be given by these two outside numbers, right? The number of rows of the left matrix by the number of columns of the right matrix will be the size or the dimensions of the product. I'll go through examples of this. All right, so all we're asked to do here, and I'll write these out, and then we'll actually, I'll come back to some of these examples and we'll talk about, the actual products. So I'll pull up some paper I'll just put it on the same screen here. So you see, for part A there, they have the left matrix is a 2x3 matrix, right? It's a 2x3 matrix being multiplied by a 2x2 matrix. It's a 2x3 on the left, 2 rows, 3 columns, and a 2x2 on the right. Do you see how these inner two numbers are not the same? There are 3 columns of the left matrix, only 2 rows of the right. These need to be the same. Since they're not the same, the product of these two matrices cannot be taken. We haven't seen how to yet, but the product will be undefined. Right. And you see that when I scroll down here, see the product of matrices with 2 by 3 times 2 by 2 is undefined. All right, oh, I got it covered by my paper. Sorry, it's undefined for part A. Okay, oops. Yeah, bring it back. For part B, all right. See, part B, that's a 2 by 3 matrix multiplied by a 3 by 2 matrix. So look at those inner two numbers when you write the sizes. Right? Again, the number of columns of the left matrix is the same as the number of rows of the right matrix. If those two numbers are the same, then you can do multiplication. And what would the size of the product be? The size of the final result will be these outer two numbers. So these are the dimensions, or the size of the product, will be a 2 by 2. Right? Will be a 2 by 2, those two outer numbers. Right, so a 2 by 3 times a 3 by 2 will be a 2 by 2 matrix. And lastly, in part C, you see there's a 2 by 3 matrix multiplied by a 3 by 3. So again, would I even be able to perform matrix multiplication based on these sizes? Well, yes. Again, the inner numbers here are the same. The columns of the left matrix is the same as the number of rows of the right matrix. And then what's the size of the final result? What would be the size of the product? These outer numbers, right? The number of rows of the left and columns of the right. So a 2 by 3 multiplied by a 3 by 3 will end up being a 2 by 3 matrix. Okay. All right, and again, they kind of rattle. You can read that all here as well. All right. All right. So here, your participation activity is select the matrix by which the given matrix can be multiplied with the given dimensions and give the dimensions of the result. So this is a 2 by 2 matrix. All right, this is a 2 by 2 matrix. So, all right, let me write this up here. If I have a 2 by 2 matrix, that means it needs to be multiplied by a matrix with 2 rows. 2 by whatever. It doesn't matter what the number of columns are. The number of columns here will only help me determine the size of the final product. But if there are 2 columns in the left matrix, there's got to be 2 rows in the right matrix, the matrix I multiply it by. So looking here, this is a 2 by 2 matrix. In order to multiply it by another matrix, that second matrix has to have 2 rows. So this has 1 row, this has 3 rows. You couldn't multiply by these on the right. You could only multiply by this on the right. And that's a 2 by 2. All right, that's a 2 by 2, meaning the result would be a 2 by 2, right? The outer numbers would be the resulting size. Okay. And I click on that and you see that coming up here. Okay. All right, so hopefully pretty simple. So this one's a 2 by 3. It's got 3 columns. So a matrix I multiply on the right side by has to have 3 rows. So only this matrix down here, it would end up with a 2 by 1. There's a 2 by 3 times a 3 by 1 would be those outer numbers for the resulting size, 2 by 1. All right, and then you can finish that off. All right, and then here, determine the size of the matrix product. This is a 1 by 3 times a 3 by 1. So those inner numbers are 3's, the outer numbers are 1's. This will end up being a 1 by 1 matrix. But this is a 3 by 1 times a 1 by 3. 3 by 1 times 1 by 3, those two outer numbers are 3s. This will end up being a 3 by 3 matrix. Okay. And they even have a challenge activity where you have to figure it out. You know, now you got to pay attention to the order, right? You saw in this last participation activity, see, the order that matrices come in matters. See, this product would end up with a 1 by 1, but you just switch the order of the matrices, you end up with a totally different matrix of a totally different size. That's not always going to happen, but still, like, just pay attention. The order matters when you multiply matrices. So here, you know, A is a 2 by 5 matrix, B is a 5 by 3 matrix. So again, what's the product of, what's the size, what would be the dimensions of A times B? Well, the columns of the left matrix is the same as the rows of the right matrix, 5 and 5, so that's good. So we'd have outer numbers, it would end up being a 2 by 3. Right? It would end up being a 2 by 3 matrix would be your final result. And I believe that's all of these, just stating the size. So this is the other way around, where I have A is a 5 by 3. The product of A and B is a 5 by 4. So that means B would have to be a 3 by 4, right? Because a 5 by 3 times a 3 by 4 would be a 5 by 4. B would have to be a 3 by 4. And again, you can figure these out. Those were the size requirements. All right, so now we get into how do you actually perform matrix multiplication. All right. So matrices are multiplied using the row column rule. Right? If the product AB is defined, right? So if all the size requirements are met, right? The columns of the left matrix is the same as the number of rows on the right matrix. If the product AB is defined, the entry in row I, column J of the product AB is the sum of the products of corresponding entries of row I of matrix A and column J of matrix B. And they highlight this here. All right, so I'm actually going to go through and I'll write this out and maybe even show you the animation, because the animation also takes it through one step at a time. All right, and you can see this written out in summation notation here if you wish, but I'm going to write out this participation activity and show you how did this matrix, see, I have a 2 by 2 times a 2 by 3 ending up being a 2 by 3, but how did they get all these entries in the 2 by 3? All right, so I'll come back. All right, so again, here's the matrix product we're asked to find in the participation activity there, or that they're showing us. So like I said, the size requirements are met, right? The left matrix is a 2 by 2, right? 2 rows, 2 columns. The right matrix is a 2 by 3. Okay, so those inner numbers are the same. The columns of the left matrix is the same as the rows on the right matrix. So the size requirements are met. Then the resulting product would be a 2 by 3, right? Those outer numbers. So the resulting product is a 2 by 3. And I'll make a little thing that's a 2 by 3. You know, so we have 6 spaces to fill, 6 entries, right? There's 2 rows, 3 columns. There are 6 entries to fill. All right, so I'm going to call these matrices some letters here. So this matrix I'm going to call matrix A, right? This 2 by 2 matrix. Pardon me. This matrix I'm going to call matrix B, right? The 2 by 3 matrix. And then this matrix is going to be just AB, right? The product AB. Right? So here's how this row column rule works. How do we actually perform matrix multiplication? So to do the first AB and do the first row, first column. All right, the first row, first column, AB 1 1. I guess I don't need the comma there. Right? So here's how you do it. For the first row, first column of AB, the product, I take the first row of A and multiply those entries with the corresponding entries of the first column of B. All right, so let me show you what I mean by that. So I take the first row of A. Here it is. And you go from left to right. The first entry is 2. The next one, the second one, is -1. And I line it up, I correspond it to the first column of B. So it's a row from the left matrix along with a column from the right matrix. And this goes top to bottom. So the first entry of this column is 5, the second entry of this column is -1. So it's just you add up the products of corresponding entries. So you say I take the first entry of A, row 1 from A, the first entry of row 1 from A is 2, and I multiply this by the first entry of the first column of B, which is 5. And then I keep doing this, and then you keep adding these products. Then I add the product of the second entries. The second entry from the first row of A is -1 times the second entry of the first column of B is also -1. And that's it. I'm done with the row, I'm done with the column. There are no more entries. And what is this product? This sum. This is 10 plus 1, 11. All right, so the first row, first column entry of AB is 11. Right. So let's move on. How about the first row, second column entry? So how about AB, the product, and then 1, 2. So again, this means I'm multiplying entries and then adding them from the first row of A, first row of the left matrix, and the second column of B. Right. So I've already got the first row of A circled. Now I'm working with the second column of B, right? Ignore the first column. And I'll just write this out here without changing colors. So take the first entries, 2 times 1, plus then the second entries, -1 times 0. And this is 2 plus 0, or just 2. So the first row, second entry of the product, AB, is the number 2. And I've got 6 of these. Right. Keep the AB up there. So now how about this one? What's in the product A times B, this matrix here, what's the first row, third column entry? So AB with a subscript of 1, 3. So again, this just means, I'm going to do this row column rule with the first row of A and the third column of B. So I've already got the first row of A circled. Now I'm looking at the third column of B, this 2, 3. So row column rule, I just multiply the first entries, 2 times 2, the first row of A, third column of B, 2 times 2, plus, and then multiply the second entries, -1 times 3, from the first row of A, third column of B. This is 4 plus -3, that's 1. So the first row, third column entry of the product is 1. All right, so it's a little tedious, it takes a little time. So now I'm done with the first row, right? All these had the first row of A, or the first row of the product here. I'm going to move on now to the second row, right? Because I still have 3 more spots to fill. Second row of this product. Right? So now I'm working. What's A times B? What's the second row first column entry? So again, these numbers mean what the second. So I go with the second row of A. Now I'm working with this row. Now I'm working with the row 0, 4. Again, the first, it goes left to right. First entry 0, second entry is 4. And the first, back to the first column of B. So second row of A, first column of B, which is this 5, negative 1. And again, it goes top to bottom. So I multiply the first entry, 0 times 5, plus multiply the second entries, 4 times negative 1. And this is just 0 plus negative 4, that's negative 4. So negative 4 is the second row first column entry of the product of A and B. And I guess I got just 2 more. So in the product AB, what is the second row second column entry? And now I'm looking at the second row of A, 0, 4, with the second column of B, the 1, 0. So first entry, 0 times 1, plus the product of the second entries, 4 times 0. And this is just 0 then, 0 plus 0. So the second row, second column entry of the product, AB, is 0. All right, then finally, there's only 1 more space to fill. Second row, third column. So what's in this product, A times B, what's the second row, third column entry? So again, I take the second row of the left matrix A and match it with the third column of the right matrix B. So 0, 4 from A with 2, 3 from B. Right? Second row, third column. So 0 times 2, right, the first entries, plus the second entries, the product of the second entries, 4 times 3. This is 0 plus 12, that's 12. And there you have it. This 2 by 3 matrix is the result. This is the product of this 2 by 2 and this 2 by 3, right, with 11, 2, 1, negative 4, 0, 12. And I'll put it in a little circle or something, a little bubble. All right. Now you can also have again, there are going to be problems in my first exam at least where I'm going to ask you to actually, do this by hand like I just did, show me every entry the long way. But you can also do it on the calculator and check yourself. Okay, so I'm going to do this. I'm going to enter this matrix A and this matrix B on my calculator and show you the product. So I'll be right back with that. Alright, so you see the calculator pop up here. I have entered matrix A, see as a 2 by 2. I entered these entries, and I'm not going to, you've seen me do it in a bunch of videos by now, so you know how to enter a matrix. Hopefully go to the edit. And then matrix B, number 2 here, is this 2 by 3 with these entries. Alright, so I go on my main screen, enter matrix A, times, and then back to the matrix, and then matrix B, and then you'll hopefully see this 2 by 3 matrix show up with the 11, 2, 1 first row and negative 4, 0, 12 second row. And look at that, right? It's exactly the same, and it should be, right, if I did everything correctly. And let me show you what happens when you put it the other way around. What if I did matrix B times matrix A, put B times, now that would be a 2 by 3 times a 2 by 2. You can't do that. All right, the dimensions are wrong, and you'll see an error come up here. See dim mismatch. Dimensions are wrong. Dimension mismatch. So just be careful. Remember that order matters. The order matters a lot when you're multiplying matrices. Alright, so back here, you can watch the animation. I'll actually show you, like, I think it does this nice 5 little step thing where it shows you, are the dimensions good to multiply? Yes. What would be the result of the product? Right, it would be a 2 by 3. Okay. Then it starts going into the row column rule. See, first row, first column, see how it kind of circles the first row on the left, first column on the right, takes those products, adds them up like I was doing, and it does that for all the rest of the entries. Right now, your first row, second column, it moves over to the second column on the right, first row on the left, second column on the right, and then the rest of it just kind of slides all the way through, filling in every single entry. The way I did on paper earlier, it's just you see an animation here. Maybe it makes it a little more clear what I was doing. So I'd recommend watching that and making sense of the steps. All right, so I'll do that one more time. Let's multiply these matrices. Right, again, by hand. Right, by hand. Right, so we're going to multiply these matrices. So this left one is a 3 by 2, right? This is a 2 by 2. So you got the inner numbers are correct. They're matching. So I can multiply these. And the resulting product then would be a 3 by 2, those two outer numbers, right? Oops, sorry, I dropped the marker there. So the resulting product would be a 3 by 2. So I'm going to draw in an empty 3 by 2 matrix. So there are, again, 3 times 2 is 6. There are 6 spaces to fill here. So I'm going to go, what's the first? I'll do first row, first column entry, right? 1, 1. First row, first column entry. Maybe I'll put a comma here so it's actually separate. So first row on the left with the first column on the right, that'd be, again, negative 1 times 1. The first entries plus 0 times 3. That's negative 1. Okay. And then let's go first row, second column of the product. So again, first row on the left with the second column on the right from top to bottom. I'm just going to, that's negative 1 times 0 plus 0 times 2, that's 0. Right. Now I'm moving down. Here's the second row, first column. So now I'm looking at the second row on the left, first column on the right. So 0 times 1 plus 2 times 3, that's 0 plus 6, that's 6. I'm just going to kind of just say what they are. That's 6. Then the next space I'm trying to fill, second row, second column. So second row on the left, second column on the right is 0, 2 with the 0, negative 2. 0 times 0 is 0, plus 2 times negative 2 is negative 4. 0 plus negative 4 is negative 4. Then moving down, we have the third row, first column. So now I'm working with the third row on the left, first column, 1, 3 on the right, negative 3 times 1 is negative 3. 4 times 3 is 12. Negative 3 plus 12 is 9. 9 there. And then finally, third row, second column. Third row on the left with the second column of the right. Negative 3 times 0 is 0. 4 times negative 2 is negative 8. 0 plus negative 8 is negative 8. All right, and then there's your resulting product. All right, here's the product of these two matrices. Okay. So again, hopefully this row column rule doesn't seem, it's a little trickier than a matrix addition and scalar multiplication. It's a little trickier, sure. But hopefully just keep track of what row from the left matrix am I using and what column from the right matrix am I using. And you fill in all these blanks there. The A, B, C, D, E, F are these, what are the entries of that matrix? You saw me just do it. All right. All right, so this is another example where it's just, now this is an example to show you that, remember I've been saying it, order matters, right? Matrix multiplication is not commutative, meaning that A times B, right, is not going to be the same all the time as B times A. And you can see that with this example here. See, if I take these matrices, A times B is this matrix with negative 6, negative 8, 0, 1, 0, negative 1. But B times A is negative 1, 0, 6, negative 6. These are not the same matrix. So A times B is not the same in general as B times A, when you're multiplying matrices. So that is a huge thing to remember. Okay, and I've been saying it a bunch. Order matters. Right? Order matters. Okay. We got some more examples. Again, I'll let you play with these. Right, yeah, you can start. That's all about how, all about size. Are the sizes correct for multiplication, and what would be the product if I could multiply them and stuff like that. So I'm gonna leave that to you. And I'll show you what the challenge activity looks like to start. There are 6 of these. So here, select the row of matrix A and the column of matrix B that would be used to find the entry, AB25 in the product AB. So this is the product, second row, 5th column. Second row of the left matrix, so the second row, I would use this row of A with the 5th column of B, the 5th column of B. I would use these and I'd multiply all these entries by all these entries and add them up to get the second row, 5th column entry of the product. And that's all they asked to do in that one. Pretty simple. So the next one is actually do the multiplication. All right. Now again, pay attention to the order. All right. It's A times B, not B times A. So A times B, the first row, first column entry, again, -1, 0 with 1, -2, do that row column rule. You get -1, right, -1 plus 0. Then first row on the left with the second column, so I go -1, 0 with 0, 1, you get 0, and then row column rule, you get 0 plus 0 or 0. Then for the second row, first column, do second row on the left, -2, 1, with the first column on the right, 1, -2. You get -2 plus -2, that'd be -4 for that entry. And then the second row, second column, you're doing -2, 1 with 0, -1. So 0 plus -1 or -1. All right, and I fill in all those, check to see that my product is correct, and it is. And great. Yeah, so here's another one. Now this one, you don't have to fill in all. Let me just have to fill in these 2 here. Now this is, this is A times B, a 2 by 3 times a 3 by 2. So this time you'd have 3 entries to multiply. So I'll do this last one. So first row, first column. So first row of the A, -2, 0, 1, with the first column of B, do that row column rule. So -2 times -2 is 4, plus 0 times 2 is 0, 4 plus 0 is still 4, and then plus 1 times 1 is 1, 4 plus 0 plus 1 is 5, so I have 5 there. And then this entry is the second row, first column. So I do second row of the left with the first column of the right. Second row of A with the first column of B, and do that row column rule. You have -4, -6 is -10, and then -1 is -11 for that entry. And then I check, and great. All right, so I didn't have to fill in the entire product there. All right, and then there's more for you to do. All right, the identity matrix in matrix multiplication. Now you've seen an identity matrix already, right, in previous videos. That's where you have it's a square matrix, right? It's a same number of rows as columns, and it's got ones down the main diagonal, right, where the row numbers and column numbers are the same. The first row, first column entry, second row, second column entry, and so on. The main diagonal entries are all 1. And then every other entry off the main diagonal is a 0. And the n by n, again, you've seen all this already in a previous section. The n by n identity matrix is often denoted by I, capital I with a subscript of n. Right. The identity matrix is so named because multiplying an m by n matrix A by im on the right or in on the left yields A. This should be the other way around. See how they, see here IM's on the left and IN's on the right, so they should have switched these words. I'll leave a comment for people who wrote this. But I have an m by n matrix times, A, identity matrix times A equals, A times the n by n identity matrix. All that's just equal to A. So the lesson here is when you multiply a matrix by an identity matrix, if the sizes are correct, right? If the sizes are correct, you'll end up with just the matrix you started with. Right. So I give you an example here where they do multiplication. See, this is here's a 3 by 2 matrix multiplied by the 2 by 2 identity matrix, and you end up with that matrix back, right? That 3 by 2. And here's the 3 by 3 identity matrix times the 3 by 2, and you end up with that 3 by 2 again, the same exact matrix back. Right? So when you multiply by an identity matrix, you end up with the matrix you started with. All right. So I'll work through a couple of these here. So the identity matrix I2 is this. Yes, this is the 2 by 2 identity matrix. 1's down the main diagonal, 0's everywhere else, so that's true. Matrix A can be multiplied by I2 on the left side. Well, A is a 2 by 2. So you can multiply by a 2 by 2 on the left side. That'd be true. Right? As long as the dimensions are correct for multiplication. Right? B can be multiplied by I2 on the right side. Well, B is a 3 by 2. Right? B is a 3 by 2. On the right side, I'd have to multiply. I could multiply by a 2 by 2. That would be fine. The dimensions would match. You know, the dimensions would be correct for multiplication. And I might as well finish it. C is a 2 by 3. So if I multiply on the right, I have to multiply by a matrix with 3 rows. This only has 2, so I can't multiply C by I2 on the right. Right? So that's false. And pay attention to dimensions, the sizes of the matrices. And this is the same thing here. You just fill in which identity matrix would make the statement true. You know. So like for example, C is a 2 by 4. So in order for C times I to be equal to C again, this I would have to be the 4 by 4 identity matrix, this I4. Right, and again, it's just really paying attention to the sizes. And they show you the example there. You know, C times the 4 by 4 identity matrix would just be C again. Right. And then we get into some properties of matrix multiplication. Right? These things are true all the time for as long as the size requirements are met. Right? If the size requirements are not met, then you can't multiply. So again, let A be some m by n matrix, and B and C be matrices of appropriate sizes such that sums and products below are defined. Right? And R be a scalar. So I'll just read these off. I'm not going to go through the proofs. Right? There is an associative property of matrix multiplication. So if you multiply 3 matrices, right? Again, as long as the size requirements are met, if you multiply 3 matrices, it doesn't matter which 2 you do first. You can multiply the first 2, then by the third, or you multiply the second 2 and then by the first on the left. But you got to keep them in the same order, though. Remember, order matters. You got to keep the matrices A, then B, then C. You can't switch, B with C or C with A. Right? But there is an associative property. There's a left distributive. If you multiply the sum of 2 matrices by a matrix on the left, you can distribute that matrix, but it's got to be on the left side. Right? The order matters. So if it's on the left, it's got to stay on the left. And the same thing for the right. If it's on the right and you distribute, it's got to stay on the right of those matrices in order for multiplication to stay the same and stay defined. You have an associative property of scalars in matrix multiplication. So if you have a product of 2 matrices, A and B, and you multiply it by a number, a scalar, you can move that number to any of the matrices you wish. So you see, if I do A times B first and then multiply by the number, you get the same result as if you multiply A by the number and then multiply by B. Or you multiply B by that number and then multiply by A on the left. You get the same result. So basically you can move scalars around in matrix multiplication. And then this one here is why I stated up earlier about the identity matrix. Right? If you multiply by an identity matrix, you should get the same matrix back as long as the sizes are correct. Right? And I got some proofs and stuff and examples. Again, it's all you've seen me do multiplication. Right? So I'll leave that stuff to you. All right, and then let me show you what the challenge activity looks like. Now this is see, it's a times I, so it should just be a. Right. Again, the sizes are fine. You can multiply a 2 by 2 by a 2 by 2. So a times the identity should just be, a. 4, 1, negative 3, 5. And here, again, these are all 2 by 2, so the size requirements are fine. Now you can distribute the I if you want, but really you can just add A and B, and then if you multiply by I, an identity matrix on the left, it's just going to be A plus B. So the result will be whatever A plus B is, which is really simple. All right, and again, I leave the rest to you. All right, then the last part, and this is where I'm going to go back to those charts, that figure from the very beginning of the section. Because sometimes numbers have meaning, right? Numbers have units and actually mean something. So if you read through this example here, the table below gives the gross domestic product, or GDP, for Ohio and Indiana for the first quarter of 2015 and the first quarter of 2016. All right, so these are in millions of dollars. All right, little chart. And this is like a 2 by 2 matrix. So expressing the data in the matrix, gives me, like I said down here, you got G for gross domestic product. First row is for Ohio, second row represents Indiana data. First column represents, the first quarter of 2015. Second column represents the first quarter of 2016. So the difference between the GDPs of each state in the first quarter of 2015 and the first quarter of 2016 can be found by multiplying the matrix by, the 2 by 1 matrix, negative 1, 1. You see why that is? Remember the row-column method, the row-column rule? If I multiply this matrix by the matrix with this negative 1, 1 column, see, I do the first row with it's a 2 by 2 times a 2 by 1, which would end up with a 2 by 1. You see the final result is a 2 by 1 here? And you'd be taking the first row with each row with this column and doing the row-column rule. So I'd take 610,928 times negative 1 plus 615,573 times positive 1. So it's the opposite of this value plus this value. That's just subtraction. If you take the opposite of one value and add another, that's just subtracting these two. So this value here, this 4,645, that's just the difference between these two first row values, or the difference between the first quarter GDPs for these 2 years in Ohio. Right? And then the second row, this 5,432, that's just the difference between the GDPs for each year in Indiana. Right. Okay. So you got to really just, again, just numbers can mean something, and matrix multiplication can help us determine certain things like differences here and whatnot. All right, so I'm going to go through this participation activity, and then I'm going to go back to the very beginning. Right? There was that figure in the very beginning that hasn't been brought up since, and we'll talk about what it means. All right, so this is similar to the previous example. Right? It says total retail sales in millions of dollars and some years. Right? Now, this isn't lining up, so unfortunately, the first column of numbers here, these two numbers, 106,599 and 491,360, those are for 2007. And then the 95,364, 510,033, those are for 2009. And these are total sales for electronics and appliance stores in 2007 and 9, the first row, and then for grocery stores in 2007 and 9. Right? So expressing the data from the spreadsheet as matrix S. So they're calling this 2 by 2 matrix S. What is the product of S times negative 1, 1? So this is kind of like up here with the G times negative 1, 1. See, all this is going to give me is the different, it's a 2 by 2 times a 2 by 1. It'll give me a 2 by 1. So the only one that actually matches the sizes is the second one. It's a 2 by 1. And you see that these values are just the differences. It's just the opposite of the first value in the row plus the second value. All right, so basically it's the second value minus the first value. Gives us a difference in sales from 2009 to 2007 for these kinds of stores. Right. The difference between total resales in each category for 2007 to 2009. Maybe that's the change, right? Because it's negative if it's going down. Because you see how the first one's negative, right? It's a negative. It went down $11,000 or 11,000 million or $11 billion. And the change, this one went up, so it's a positive. So I guess it's better represented by the word change instead of difference. The change in total resales sales for each category. This one, notice it's a little different. S is this again. S is this 2 by 2, but now I'm multiplying by the 1 by 2, right? 1 by 2 on the left. So I'm going to end up with a 1 by 2. So it's either one of these. But this time it's negative 1 times S. So I'd be taking negative 1 times the top value in a column plus the bottom value. So what we're going to be getting here is the difference between values in the same year, right? Not in the same row. We're going to be getting the difference in the values in the same year or in the same column. So you see that difference between these two is about 380 some thousand. Right, so it's definitely this one here. Right? And again, you can do that by hand or with a calculator or whatnot. And again, what does it mean? It's the change in retail sales, not for each category, but it's the difference between them in each year. Right? It gives me the difference that happens down each column. And again, you can kind of reason that out. All right, sorry to rush through that, but I want to get back to this first, the very top of the section. Right? So, like, what do these numbers mean? Right? So here I have a 4 by 3 matrix. Here I have a 3 by 5. So, what would it mean to multiply these? Right. Now, there's only one way they could be multiplied. And then what would that multiplication give us, right? So I'm going to write these out and show you. All right, so I've written these matrices out. You have the matrix for the sales made, or it was sales goals, but let's just say it's sales made. So Team South, they sold 50 of product A, 75 of product B, 150 of product C. Team North sold, 45 items of product A, 30 of product B, 90 of product C, and so on. And that's a 4 by 3 matrix. And then we had a matrix representing the costs. What did it cost to make and ship? Your cost for the materials to make product A, the labor to make it, the packaging, and the shipping of these products. So this is for each item of product A. So every item of product A, costs $25 for the wood, $5 for the paint, $7 for the labor to make it, $3.25 for the packaging, and $7 for the shipping. And that's for one item of product A. And same thing goes for one item of product B, one item of product C. So what is the product of these two matrices going to mean? What is the product going to give us? Now, notice the sizes. All right, when I talk about the product, there's only one order. Right, there's only one order I can actually do it in. Right? I can't multiply this matrix, the cost matrix. I can't multiply the cost matrix by the sales matrix because the sizes don't match, right? Because you'd have the cost matrix times the sales matrix. That's a 3 by 5 multiplied by a 4 by 3. Those two inner numbers don't match up. The number of columns of the left matrix is not the same as the number of rows on the right. So cost times sales has no meaning. Right? Cost times sales would be undefined. But the other way around has some meaning. Right? Sales times cost. The sales matrix times that costs matrix. The sales matrix is a 4 by 3 times the cost matrix is a 3 by 5, right? So the resulting product, right, these two inner numbers are the same. The resulting product would be a 4 by 5. And what does the product mean, right? So let's think about that. What would the product actually mean? All right, so I would have to take this matrix on the left, or I'm sorry, this matrix on the left. This is the left matrix. This matrix on the right. All right, so that way the sizes are correct. So what I'd be doing when I multiply, right? And in fact, let me just start writing out this product. All right. Pull this up here. Maybe a little more space here. Let's start taking this product. All right. So what is sales times costs? What would it mean? So again, it would be a 4 by 5. We saw that earlier. 4 rows, 5 columns. It's kind of going off screen there for. So how about the first row, first column? What the heck would it mean? So I'll circle these. What's the first row of the sales column? That's this here. This tells me, that again the first row is representing Team South. Right? This tells me that Team South sold 50 units of product A, 75 units of product B, and 150 units of product C. And notice how the column labels in this matrix are the exact same as the row labels in this matrix. So it makes sense to multiply sales by costs. So that's the first row of sales, and I want to match it up with the first column of costs, which would be this wood column. And doing that, and again, all this means is that one unit of product A costs $25 in wood. Is it $25 in wood in its cost? One of product B, 1 unit of product B has $40.50 of wood in it, and 1 unit of product C has $35 of wood in it. And then doing that row column rule, I would take 50 times 25 plus 75 times 40/50 plus, and then 150 times 35. Let me get this in here. 150 times 35, and this is, and I'll calculate this. Okay, and this is 9,500. And this is dollars, right? Now think about what this is telling us. Remember, South sold 50 items of unit A, where each unit of A has $25 of wood in it. So this 50 times 25, this is the cost of all the wood for all the items of unit A they sold. Right? So this is the cost of all the wood for all the items of unit A that Team South sold. And then this, the 75 times 40/50, that's the 75 items of unit B, of product B that Team South sold, multiplied by the cost of wood for each unit of product B. So this is the cost of all the wood that Team South sold for product A. This is the cost of all the wood that Team South sold for product B. And then this would be the cost of all the wood that Team South sold for product C. So this is the cost of all the wood used for the items sold by Team South. For the items sold, or the A, B, and C by Team South. So if I think about that, I can make this first row represent South, right? Team South. And then the first column, the wood cost. So the sales times cost, this is going to give me a matrix that represents cost of materials. Individual cost of individual materials, the wood, the paint, the labor, whatever, individual materials. So we have $9,537.50. And then the first row, second column, right, I would go to this column here. I'd use, again, the first row for Team South. The second column in this matrix is the paint costs. So the first row, second column of this matrix would be how much did all the paint, what's the cost of all the paint for all the objects that Team South sold. So this matrix, this product matrix would actually have a meaning. Every single entry would be the total cost of that object, of that material for that particular team. Okay. All right, so I just wanted to point that out. Right? I'm not going to do the whole matrix. There's 20 spots to fill. It's a 4x5. But I just wanted to point out that the matrix multiplication, especially when numbers have meaning in units, dollars and ounces and minutes and whatever. Matrix multiplication will have meaning. Right here, this particular product here would have a meaning. It would represent the total cost of these individual materials for the objects sold by a particular team. Okay. All right, so that's all I wanted to get out of this chart up here. Right. All right, so then again, at the very end, you have exercises, additional exercises. Some of these, right, are on your assignment 3. To do those, and you got the solutions available to you to check yourself. Again, please, I'm gonna maybe looking to see that you're doing work, not just writing solutions. Please try to do these things. I say this almost every video. Please try to work them out before you look at the solutions. To make sure you're, and then check the solution to see how you did. Because you're not gonna learn anything, and you're gonna do poorly on the exams I give you, that I post for you. If you're just copying solutions and not reading. All right. Okay, so that's it for section 2.2. This introduction to matrix multiplication here. Again, remember the size. Please remember the size requirements, and that order matters. Right? Order matters. A times B is not always going to be equal to B times A when they're matrices. All right, and hope you have a good time doing your own assignment, and thanks for watching.